Let's look now at the carrier distribution. Where exactly are these carriers in terms of energy within these bands, the conduction band and the valence band? So we can define G of E as the density of electron states, that's per cubic centimetre, within some interval between energy E and E plus delta E. And so it's going to have units of number electron volt per cubic centimetre. And then F of E is the probability that a state of a given energy will be occupied. So these are the two densities of states for C, the conduction band up here, that's GC, and the valence band down here. So G of C is going to be the density of states for the conduction band. GV of E is going to be the density of states for the valence band here. And so if we know these numbers, and we know the probability that a state of a given energy will be occupied, then we can calculate where all the carriers are in terms of energy inside the solid. So first of all, notice that these density of states functions are parabolic. There's zero at the end of the gap. If the energy is equal to EC, which is the conduction band edge, then there aren't any states there at all. And the number of states increases parabolically as we go up. So we can draw a little sketch like this that says if this is energy and these are the density of states, then within the band gap there aren't any. At this point here, which is the conduction band edge, we have actually zero states, and we increase their number, that's GC, as we go above the conduction band edge. And similarly at the valence state, they're going to go down, GV, like this. You will notice that these two densities of states don't have the same slope, and that's because the effective masses are different. There's MP here and MN here. So if the effective mass of the electrons and the holes is different, then we're going to end up with different slope to the density of states, and that can have some consequences in the way that they're populated. So we have, according to these, an infinite density of states. Actually, that's not really true, because these, as we know, these densities of states can only contain 4n electrons, where n is the number of atoms we have here. And so somehow these have to close up at the top and the bottom, and that gives us the width of the conduction band and the valence band that we looked at on the previous slide. But from the point of view of the vicinity of the band gap, this gap here near EG, they are parabolic, and it doesn't really matter too much what happens way up here or way down here, because down here is always fully occupied and way up here is never occupied. So from the point of view of doing calculations, the assumption that these densities of states are actually parabolic is pretty good. But when you do integrations and so on, you have to remember that they don't actually go on forever. Otherwise, we'd be able to populate them with an infinite number of electrons and holes. So how does the finite number of electrons occupy these states in the valence and conduction band? Well, we can define a Fermi function, f of e, which tells us the probability of occupation. So this is the Fermi function. And it says that the probability of occupation depends on the difference between the energy we're interested in and the Fermi energy, EF, the Fermi energy. We now have to define what the Fermi energy is, but once we know what that is, we can say that a given state will have a probability of occupation that depends on how far away from the Fermi energy it is. And we have a factor of temperature in here, so this is a temperature-dependent function. So what shape is this function? If I can plot it out like this, this is energy and this is f of e, then it looks something like this. It's going to vary between 0 and 1, it's a probability. As we go up to very high energies, that probability goes down to 0. There's no chance of finding an electron at very, very high energies at thermal equilibrium. As we go down in energy, the states are all occupied, so f of e is 1, and at this point here, which is the Fermi energy, we get a half. So if you put E equals EF here, you get 1/2 as the Fermi function, the value of the Fermi function. So now we know what the probability of occupation is, and we know the shape of those densities of states. So now we can work out where the carriers actually are in the conduction band and valence band. What we're going to do is multiply the two together, and we're going to say that if I have, as a function of energy, I've got GC here, that's just the occupation, that's the density of states, GC and GV, and I've got a Fermi function. Let's suppose the Fermi function is somewhere in the band gap, which is typical for these semiconductors. Then we know that we've got the tail of the Fermi function multiplied by GC up here, and so the carriers are occupying these energy states. This is where the electrons are. And down here, most things are full. We're in this part of the Fermi function, and we get some distribution of holes. So we're all full up with electrons, like this, and this is where the holes are going to be. So you can see that we have some holes in the valence band, some electrons in the conduction band, and most of them are near the band edge, but of course they're not exactly at the band edge because there aren't any states there, because G of C is 0. So we get a point here which is on the order of kT above the conduction band edge, where we have the maximum number of carriers, density of carriers, and as we go above that we can see this exponential decay which is coming from the tail of this Fermi function. And similarly, the holes are mostly around kT below the valence band edge, and they, as we go down in energy, the chance of finding holes with these very low energies gets smaller and smaller exponentially. So the Fermi function is just a statistical function. It's giving the probability of occupation whether or not there is a state there. So the Fermi function is still defined within the band gap, even though the band gap doesn't have any states in it. The width of this Fermi function is on the order of kT, around 3 kT is where most of the action is taking place, between going from fully occupied f of e equals 1 down to almost unoccupied where f of e is close to 0. So the number of electrons we can write down within some energy level, some energy difference delta E, is just f of e times g of e. So it's gc of e in the conduction band, or we could write the number of holes in the valence band in the energy range between E and E plus delta E is just 1 minus f of E times GV of E dE, like that. Because in an intrinsic material, we know that N equals P, and so the number of holes and the number of electrons that has to be the same. There's the same number of holes in the valence band as electrons in the conduction band. So if you look at this plot here, you can see that when GC and GV have the same shape, the same slope, then everything is symmetrical and the Fermi level must be right in the middle. But suppose we had a very different effective mass. Let's look at a situation like this where the effective masses are very, very different. And if I now have to have the same number of holes here as I have electrons here, then this area has to be equal to this area. And that tells me that the Fermi level is not going to be in the middle of the band gap. It's going to be somewhere higher up in the band gap so that we can have a bigger tail here to compensate for the larger density of states in the valence band. So the Fermi level is mid-gap if m star n and m star p are the same, but if they're different, then the Fermi level is going to be offset from the middle of the gap, and we'll find an expression for that a little bit later on. We can also look at the situation when we have a doped semiconductor. So in the doped case, let's suppose that n is much greater than p. And let's suppose we have a situation where the effective masses are the same, just for simplicity. If I'm going to have n much greater than p, the only way to get that is for the Fermi level to be much closer to the conduction band edge than it is to the valence band edge, so that the tail of the Fermi function extends up here and we get a much larger number of electrons. This area represents N. And down here we're at a very small number of holes. So you can see from this simple model that we've got a way of understanding both doped and intrinsic semiconductors, and also understanding what effect the difference in effective masses has on the distribution of these carriers.